So, welcome to the deep dive. We are so glad you're here today because, well, we've got a fascinating one for you.
Oh, yeah, we definitely do.
Yeah. Today, our mission is to completely demystify something called object-oriented programming, or OOP.
Right, which sounds super technical, I know.
It does. It sounds like something you'd only hear in a dark basement full of glowing screens. But it's actually the fundamental way that all modern software organizes digital information.
Mm.
We're going to look at how we move from, like, basic, messy computer code to building these highly structured digital representations of the real world.
And we're using a really cool source for this. It's a set of lecture notes from an MIT OpenCourseWare class.
Yeah, Introduction to Programming in Java, specifically the January IAP session from 2010, Lecture 4.
It's just a classic, really. These notes are fantastic because they capture that exact transitional moment that every single programmer faces.
Right. And I got to warn you, even though we're diving into computer science, the examples we're going to talk about are surprisingly human. I mean, we're talking about diaper changes,
Oh, yeah.
like 500 crying babies, and even some unexpected celebrity cameos like DMX and Slim Shady somehow made it into this MIT lecture.
They did. It's pretty memorable. But the premise here is crucial. Before we can build these complex digital worlds, we have to understand the traps that completely break them.
Yeah.
The lecture forces us to look at how a computer's memory physically manages huge concepts without just, crashing instantly.
Okay, let's unpack this.
Uh-huh.
Because before we can build anything, like actual objects,
Yeah.
we have to survive the foundational pitfalls of primitive programming. The notes open up with common bugs.
Right, the stuff that drives beginners absolutely crazy.
Exactly. And the first one is the difference between an array index and an array value.
Oh, yeah. This one chips up almost everyone. Because, human brains are wired for context, right? We just understand things implicitly.
But compilers have zero context.
Exactly. None. So an array is just a list of items. So you have an array called values, and it holds three numbers, 99, 100, and 101. In Java, counting starts at 0. So the first location is spot 0, the second is spot 1, the third is spot 2. Those are your indexes.
Right, the index is the location, and the mistake people make is confusing that location with the actual data sitting inside it.
Right.
Like I was thinking, it was basically like confusing your street address with the actual house you live in.
That's a great way to put it.
Yeah, like if I tell you I live at number 0 on my street, that is just my index. That doesn't mean there are 0 people inside the house.
No, not at all.
There could be like 99 people having a massive party in there. The address is just how you find the house. It's not the contents of the house.
And the thing is, the computer is entirely literal. If you tell it to do math on the street address, when you actually meant to do math on the people inside, it will happily do it. It just executes the command.
And it doesn't even tell you it's wrong.
No, it breaks silently. You get a mathematically perfect answer that is just entirely wrong for what you wanted.
That is terrifying.
Yeah.
Just a silent failure. And that actually carries over to the next big trap they talk about, which is formatting. Specifically, curly braces.
Ah, the curly braces.
The notes show this simple little for loop. It's designed to print the word hi 5 times, but the programmer forgot the curly braces, the little brackets that group the commands together.
Right.
Yeah, so the code just says for loop, and then under it, indented nicely, it says print hi, and right below that, print bye.
And to a human, that looks totally fine. You look at that neat indentation and you assume hi and bye are both part of the loop.
Right, because we read visual space. But the computer doesn't care about your spaces at all.
Not even a little bit.
Without those curly braces creating a hard boundary, it only loops the very first line.
Yep.
So it prints hi 5 times, and then only when it's completely done with that, it moves on and prints bye once.
And this is exactly why the notes hammer home this one vital keyboard shortcut, Ctrl-Shift-F.
Oh, Ctrl-Shift is a lifesaver.
It really is. It auto-formats your code based on how the compiler actually interprets it, not your optimistic indentation.
Right.
So if you have a logic bug hidden in there, hitting Ctrl-Shift-F strips away the illusion. It shows you the true structure.
You definitely need that clarity, especially for the variable initialization trap they bring up next. This one is so sneaky.
Oh, the minimum value problem.
Yes. Imagine you're writing a little program to find the minimum value in a list of numbers. The notes give this classic example where someone declares a variable called min and sets it to 0 to start.
Makes sense, right? Set a baseline.
Right. Then the code loops through the array, comparing each number to min. If the array number is smaller, it becomes the new min.
Standard operating procedure.
But, and I want you to think about this, what if the array only has the numbers 1, 2, and 3?
Huh. The literal nature of the machine strikes again.
Yep.
It looks at the first number, 1, and asks, is 1 less than my current minimum, which is 0?
Yeah.
Is 2 less than 0? No.
Right.
Is 3 less than 0? No.
So at the end of the loop, the computer proudly declares that the minimum value is 0.
Even though 0 was never even in the data set.
Exactly. You accidentally anchored the whole search to a phantom number.
And the solution they offer is purely structural. Instead of guessing a starting number like 0, you set your baseline min to the very first item that's actually inside your array, like val 0.
Or they say you can set it to integer.ag_VLU.
Right, the highest possible number the system can hold. That way, any real number in your data is guaranteed to be smaller and trigger the update.
It's all about tracking what the machine is actually seeing.
Yeah.
Which is why their ultimate debugging tip is just sprinkling system.out.println everywhere.
Yes, force the compiler to print its internal monologue to the screen.
Just yell your thoughts at me.
Exactly. When you see the console print out current minimum is 0 while looking at a list of positive numbers, the flaw loses its camouflage. You stop guessing what the code should do, and you see what it is doing.
But, this brings us to a massive structural bottleneck. Because if tracking simple variables is this fragile-like, if a 3-item array is a minefield of typos, how do you scale up?
You really can't. Not with primitives.
Right. You can't just use basic primitives to track a complex ecosystem. And that's the core transition in the lecture, moving from basic debugging to what they call the 500 baby problem.
Which is such a funny way to frame it, but it's so true.
It's amazing. They point out the sheer absurdity of the primitive approach. Like, say we have a baby named Alex in a digital nursery. We make a string called name Alex and a double called wait Alex. Manageable, right?
Sure, for one baby.
But then David arrives. So we make name David and wait David. But what if a second David arrives?
The dreaded second David.
The notes literally show the programmer typing string named David 2 and then just writing the comment terrible right next to it.
Because it is terrible.
It is. The computer has no concept that name David 2 has anything to do with wait David 2. They're just loose strings floating in the abyss.
Now scale that up. Imagine a nursery with 500 babies.
Oh my gosh.
And you've got nurses, feeding schedules, medical records. You'd have thousands of stray variables like wait David 499 or nurse 3 name. It's a chaotic nightmare.
It's totally unmanageable, which is exactly why object-oriented programming, or OOP, was invented. It's not a style choice, it's a structural necessity.
Exactly. OOP was designed to represent the real world. In reality, a baby isn't just a floating name and a disconnected weight. Those traits belong to a unified entity.
Right.
OOP groups those loose variables together into a single object.
And we do that by creating a blueprint, which Java calls a class. So the lecturer builds this baby class, and I love the exact attributes they list. The feels right. I have a string for name, a Boolean for Ismail, a double for weight, another double for decibels to track how loud they cry, naturally.
Naturally.
And crucially, an integer for numpoops.
Can't forget numpoops. But really, that class is just potential. It's a blueprint. It's saying whenever we make a baby in this software, it will have these bundled traits.
But a blueprint can't cry. It can't eat. So how do we bring it to life? We use the new keyword. A class is the idea, but the instance is the reality.
Right. When you type new baby, you are telling the computer's memory to carve out physical space for an actual real instance based on that blueprint.
But you don't want a system full of blank, generic babies. You have to assign traits. So how does that happen?
You use a constructor.
A constructor, okay.
It's a special setup tool. It shares the exact name of the class. So when you make the instance, you pass the details through the constructor to set it up.
And the notes use a great example, Shiloh Jolie Pitt.
Very 2010.
Very 2010. The syntax is new baby, Shiloh Jolie Pitt, true. The constructor catches that string and that Boolean, and boom, you have your instance.
But an object isn't just data. It has behaviors, too. Methods.
And the methods they list are hilarious. There's a say hi method that prints, hi, my name's Lim, shady.
Obviously.
And then there's the poop method. When you run it, it adds 1 to numpoops and prints. Dear mother, I have pooped. Ready the diaper.
It's funny, but it perfectly shows encapsulation. The method is changing the internal state of that one specific baby without messing with the rest of the program.
Yeah. And here's where it gets really interesting. I was looking at the eat method in the notes. You pass in a double for the weight of the food weight.
Right.
If a class was just a dumb bucket of data, it would just add that number to the baby's total weight, right?
Right, just simple math.
But the method has a safety check, an if statement. It checks that the food weight is greater than 0. and that it's less than the baby's total weight.
It's a boundary check.
It's like a bouncer for the data. If a glitch tries to feed the baby like -5 pounds of food, the object blocks it. The class has its own built-in logic to protect its data.
The messy logic is kept inside the object. The main program doesn't have to check everything. It trusts the object to manage its own boundaries.
But wait, this creates a huge physical problem for the computer. If a primitive number fits into a tiny little memory slot, a baby object with strings and methods and booleans is huge. How does the computer store that?
It's a completely different mechanism. And this brings us to one of the most crucial concepts in Java, the difference between primitives and references.
Yes. The notes use this brilliant analogy. They say, think of a variable as a fixed size cup.
Right, just a standard cup.
And primitives,
Yeah.
like an int or a double, they're small. They fit perfectly inside the cup. The variable basically is the value.
But objects like our baby class, they're way too big. They can't fit in the cup.
So what goes in the cup? A bigger cup.
No, the cup stays the same size. The massive object is stored somewhere else entirely in a huge pool of memory called the heap.
Okay.
What goes into the cup is just a reference. It's a tiny number that locates the object.
Oh, it's like a map to the house.
Exactly.
The object is this giant mansion out in the memory heap, and the variable cup just holds a tiny piece of paper with the directions to get there.
You're holding the map, not the house. And understanding that completely solves the Shiloh 1, Shiloh 2 dilemma from the lecture.
Oh, this part blew my mind. Okay, imagine you write code to make a new baby instance.
Oh.
Baby Shiloh 1 equals new baby Shiloh.
Okay.
Then on the next line, you make another one. Baby Shiloh 2 equals new baby Shiloh. So if you ask the computer, does Shiloh 1 equal Shiloh 2, what happens?
The computer says no. Strictly false.
Which feels so wrong. They have the exact same name, the exact same starting weight.
They have the same furniture, yeah. But the symbol doesn't check the furniture.
Right.
It looks inside the cups, and inside the cups are the references. Shiloh 1 holds a map to a house on the north side of memory. Shiloh 2 holds a map to a different house on the south side.
So it just checks if they are the exact same physical house.
Yeah.
Not if they look similar.
Precisely. If you want to change the baby's data, you have to follow the reference map.
And this leads to an even wilder realization.
Uh-huh.
What happens if you write baby 1, baby 2?
You aren't copying the baby.
No, you're just photocopying the map. Now, both variables point to the exact same house.
Right. So if you trigger the eat method on baby 1 and then you check the weight on baby 2, the weight went up.
Because they're looking at the same house. Such a paradigm shift. You aren't throwing heavy objects around. You're just passing out lightweight directions to a shared reality.
It is, but, sometimes that isolated reality isn't enough. Objects act independently, like individual houses. But what if we need a neighborhood association?
Yeah, what if we need information that applies to all the babies?
What's fascinating here is how Java handles that. We introduce the static keyword.
Static.
When you make a field or method static, you're telling the computer that it belongs to the class itself, the master blueprint, not any single instance.
Like tracking the total number of babies born.
Right.
If you put a num_babies_made counter inside the regular baby instance, it doesn't work. Baby Alex thinks there is one baby. Baby David thinks there's one baby.
They don't know about each other.
But if we make num_babies_made a static int, we pull it out of the individual houses and put it on like a billboard over the whole nursery.
Exactly. When baby B1 is born, the blueprint updates the billboard. When baby B2 is born, it updates again. It reflects the total for everyone.
But there is a super strict rule here from the lecture. It's a one-way street. Non-static methods can use static methods, but static methods cannot use non-static ones.
Yes.
And I want you to imagine why. The lecture uses DMX to explain this, and it just clicked perfectly for me.
The DMX example is brilliant.
It really is. Imagine we build a static method called WOMI, and inside it, we try to print out the regular non-static name field, which we'll say is DMX. The computer just panics and crashes.
Because the blueprint doesn't know which baby you're talking about.
Exactly. The class is abstract. It's a schematic. It doesn't have a name.
Yeah.
Are you asking for Alex's name, David's name?
The blueprint itself can't possess an instance variable.
And realizing that finally explains the most famous line in Java. Public static void main.
Oh, yes.
Every Java program starts with that. And I never knew why it had to be static.
It has to be static because when the program first starts, no objects exist yet. The memory is empty. Oh.
So the main method has to exist on the blueprint level before any instances are built, so the computer has a starting point.
That is so cool. So what does this all mean? We started by tracking these stray primitive numbers in a tiny cup. watching our code crash over a curly brace.
And we ended up building interactive architectures.
Yeah, like the assignment 4 example from the notes. They have the students build a library class.
Right, using a book array.
You couldn't build a library with 1,000 loose string variables.
It would be the 500 baby problem times a million.
Exactly. Instead, you build a book object that holds the title, author, and a Boolean for if it's checked out. And the library class just holds an array of references pointing to those books.
When someone borrows a book, you don't move data around. You just follow the map to that book object and flip its Boolean to checked out. The array still holds the map.
If we connect this to the bigger picture, object-oriented programming fundamentally changed how humans interact with machines. It lets us build software that mirrors physical reality.
It really does.
Yeah.
It maps human logic to machine memory. And I want to leave you with a final thought to mull over. Think about that reference mechanism, the map to the house. Consider the hidden architecture of the apps you use every day.
All right.
When you update your profile picture on social media, you aren't updating millions of individual screens. You are changing the furniture in one single house on a server somewhere.
Oh, wow.
And millions of other users just hold a reference, a lightweight map pointing right to it. It makes you wonder how many invisible references in the digital world are silently pointing back to your data right now.
That is a profound way to look at it, just millions of invisible maps.
It's wild. Well, thank you all for joining us on this deep dive into the architecture of code. Keep looking for the blueprints behind the digital worlds you use every day. See you next time.